All right, we're going to talk about the basic components of a system in this video. And this is based on chapter 1 of the Meadows book, Thinking in Systems. So refer to that for more information. So a system, let's define a system first. System is an interconnected set of elements that are organized in a way that achieves something. Okay, so note that there are sort of three parts of this. So there's a set of elements. They are interconnected, and they achieve something. So these are sort of the three aspects of a system. So systems can be living or non-living. Or a mixture of those. So examples would be an atom. So an atom would not be living or contain any living parts. But let's just kind of go through these three things here. An atom, it's composed of subatomic particles. So it's made up of some things, some elements: protons, neutrons, electrons, and they're interconnected, right? They, the laws of physics control the attraction of the positive and the negative. So there's certainly the different parts of the atom are interacting with each other. And they achieve something. They achieve, there's probably different ways to look at this, but one thing they achieve is they together form a basic building block of the universe, matter. So an atom is one example. So an anthill would be an example that incorporates sort of a combination of living things, ants and the sand or the soil that they live in. So right, the elements making up the anthill system would be things like the ants, the soil that they live in, the food that they find to eat, pieces of leaves or dead bugs or not dead bugs. There's interconnections between the ants and where they live, the ants and each other. So they interact with chemicals, pheromones that send signals to attack someone that just stepped on the anthill, or it's time to do various things that ants do. So they're certainly interconnected. And they achieve something sort of greater than the individual parts, right? So they form this community, they form the anthill, they accomplish tasks as a group. So in terms of the ecosystem, the ants decompose waste or aerate the soil or disperse seeds. We could think of things like this class as a system. The elements being like the students, me, professor, the classroom, the knowledge that is exchanged, the books, videos, the university system. We're interconnected. The different elements are interconnected. So there's communication, talking, listening. There's sort of the kind of the rules of our interactions, the social norms. Information flows between us. And the class achieves something, hopefully. Hopefully there's learning, training of students for future endeavors and so forth. Human body would be another example of a system. Okay, so we can think of lots of systems. Things that may not be system. So you might be wondering what's not a system. Something lacking some of these things. So the book in the book Thinking in Systems, Meadows suggests some sand on a road that just kind of randomly on the road. Maybe something that's not a system. Although you can kind of think of ways that things like that might be a system. So maybe the sand achieves, the loose traction of a car driving through. But it's not really organized in a way that achieves something. So maybe let's put this down. Sand on a road. Maybe a dead body, maybe not a system in the way that it was formerly, so a human animal that's sort of all these parts working together to be alive and do living things. That purpose anyway is completely gone when it's just kind of a pile of meat there. So, okay, so you've got some idea of what a system is. Let's look at these parts of it in more in detail. Elements. So these can be physical, or they could be intangible. So things like knowledge, things that are a little bit hard to put your finger on. And they can often be interchangeable, the elements. So for example, different students, the class EAS 217 is still going to be EAS 217 if we have a different students, a different semester, or a different professor like last semester. It still kind of achieves the same thing, and interactions are very similar. The interconnections are a little bit more important, sort of. terms of the overall system. So changing the interconnections, let's say changing them drastically, or can drastically alter the system. You could think of exceptions to these, but so for example, if you change the pheromones in the anthill that the ants are communicating with, it could very significantly change, what the ants are doing. They might stop building their anthill. If you change the laws of physics governing the atom, it's going to be a complete change of the system, right? So the interconnections can be very, very important for the system, and so is the purpose. If we change the purpose, so the purpose or the function of the system, as I mentioned before, this is an effect different from the effect of the parts alone. So this was part of the definition of the system in a way. The different, you could think of maybe a rock as a system. So the rock is a thing that, together with all the parts glued together in the way that it is, has a different sort of function in the world than just the individual minerals by themselves. The class is hopefully something much more than the sum of the parts. It's an environment to learn in. If you're unsure of the purpose of something, of a system, observe it for a while. So we're gonna define the purpose based on how it behaves. To see how it behaves. So not how it claims to behave. So not the rhetoric. So if you want to see the purpose of our class, maybe don't listen so much to what I'm saying, but see what happens. The purpose may be unintended. So I might have good intentions, unintended, but things might go awry. So that would indicate that the system, the way the system is set up, the system does what the system does. So a poorly organized course may serve the purpose of frustrating the students. So we're gonna define that as the purposes of the system, like what actually happens, not what people want to happen. So systems are nested. So systems, the students in the class are made up of human bodies, right? And the human body is a system, and the human body is made up of organs, and the organs are systems. So there's purposes within purposes. So in a system that we could think of as well functioning, these systems more or less will align with each other. And some systems that are sort of, we could think of them as stuck, maybe have different parts that are kind of competing with each other to keep things the same. We might, and maybe going back to this point, what is the purpose? We might actually conclude, well, the purpose of the system is the purpose might be to keep things the same, even if that's not really what the people in it would like. Okay, so systems behavior over time. That's the next topic. So most of the plots that systems thinkers are interested in have, or you'll notice, there's something versus time. So the basic components that we've seen are, the first we'll call a stock. So the stock is the element of a system that can accumulate or be depleted. Meadows makes this a little bit more abstract or deep. She says it's the present memory of a history of changing flows. So an example here would be the amount of CO2 in the atmosphere. Okay, so there's the CO2 in the atmosphere has been accumulating, or some of it's been there a long time, some of it's been accumulating over time. And so what we have today, so that we could say the present memory, involves this, the history of what's happened over time to get to where we are. So on this graph, we might have X might be CO2, and we could see the level of CO2 increasing over time. And the other main element we think about in terms of system behavior over time is the flow. So the flow is the entities that make stocks increase or decrease. So examples here might be, if you're looking at a population, it could be the births and deaths that occur. If you're thinking about the amount of money in a bank, which would be that would be a stock, so the deposits and withdrawals from a bank account would be flows. In the CO2 example, the the absorption, this would be just one of many, the CO2 absorbed or released from forests. So these things all involve adding or subtracting to a stock. And we saw this in already. So some of this is review, but the stock flow diagram, we'll dig into that a little deeper here, which is also known as the level rate diagram. Shows these stocks and flows, right? So we draw a stock with a box. So the stock here, let's call it, for example, the water in a bathtub. And so this is sort of the simplest version of a stock flow diagram. So the water in the bathtub is controlled by so inflow, and we also used, so we could make one of these different symbols you could use here that control the rate. So there's water coming in, there may be, it's controlled by some kind of valve, potentially, and there's an outflow. Okay, and the water is going somewhere. We're not going to worry about that right now, and it's coming from somewhere else. We're not going to worry about that. We draw these little clouds. So we're just kind of focusing on the bathtub in this case. So there's a stock here, and then we have two flows. So the inflow could be, there could be more than one inflow. There could be a faucet. You could be putting in water by pouring water from a bucket or a hose. We could take water out from evaporation or the drain, or there could be a leak in the tub, or when we get water splashing out for some reason. So the examples, these diagrams are always going to be simplifications of a real world situation. So something to note here is that the stock is drawn as what we could call level free. So we don't say, in this diagram, we don't say full tub or empty tub, right? It's just the tub, it's the amount of water, and that gives us flexibility. It allows the diagram to work, right? So if we were to turn off the outflow, not allow any water to leave, the stock will increase and get higher. If we were to, turn off the inflow, the water would stay the same if the outflow is blocked. But if we open the drain, the water will go out, right? So the stock, we can use this diagram to think about the stock going up or down, or staying the same. So the rules here, which are basically, it's common sense, but it's worth kind of thinking about. If the flow in is greater than the flow out, the stock rises. If the flow out is greater than the flow in, the stock decreases. And if the flow in equals the flow out, we have something called dynamic equilibrium. And that is an important concept for things like, atmospheric CO2, right? How it kind of moves up and down, but it sort of stays around the same. It hasn't just been increasing or decreasing forever. Otherwise, we would have a completely different atmosphere. Some system process has maintained the CO2 level in the atmosphere over geologic time within a certain range. So if that's relatively constant, we could call that a dynamic equilibrium. Every day plants are breathing out CO2, or humans are breathing out CO2, and plants are absorbing it. But it kind of balances, on a given day. We could call that a dynamic equilibrium. Okay, so there's some properties of systems that are worth drawing attention to. Flows can change abruptly. But stocks have momentum. So another way to say this would be that flows take time to flow. So, for example, if we have a bathtub full of water, we can instantly put a plug in the drain or turn off the faucet, changing the flow dramatically. But the level of the water takes some time, right? If we open the drain, it takes a few minutes perhaps for the water to flow out of the tub. So stocks have this quality of having a momentum. So this can, depending on the situation, this can be sort of a good or a bad thing. Stocks, another sort of aspect of this, stocks allow systems to survive temporary inflow and outflow. Okay, so, I think trying to think of an example here. This can stabilize the system, right? For example, the water in a lake. We could have a really there's fish that need the lake there to survive. So it can rain a lot one month or not at all one month. So that's the flow is changing dramatically. But somehow the lake goes down, up and down a little bit, but more or less it stays there, and the fish can survive. Okay, so that's good from the perspective of the fish. And another aspect of here is that the larger the stock, so if you've got a giant lake in this example, larger the stock, the slower it will respond to a change in flow. So in terms of the example I was giving of carbon dioxide in the atmosphere, in a sense, we're lucky that the behavior of the stock is slow in a way, because um, if it adjusted instantly to the amount of CO2 we're putting in the air, the temperature would be extremely high already. Oops, I forgot an E here. On the other hand, the fact that stocks respond slowly means that the CO2 in the atmosphere that's there that we've put in is going to take thousands of years would take thousands of years to fall back to pre-industrial levels if we stopped emitting CO2. So that means we're sort of stuck with the problem of hotter climate for some time. So this is just sort of a natural behavior of systems and stocks and flows. These are sort of just general properties. So when we look at the idea for sort of dissecting these systems and these terms, is that when we look at systems we don't understand as well, we'll just kind of understand, okay, this is a stock, it's going to have this property of taking time to evolve. So we might have more patience, for example, if we understand that. Okay, and the last sort of main topic today is feedbacks. So we've introduced these before. Feedbacks are very common, one of the most basic elements of systems. So we just expect them. It's surprising if we don't have a feedback in the system. And this, in the language of what we've just learned, feedbacks occur when changes in a stock affect a flow. Okay. So in terms of the rate flow diagrams, looks something like this. There's a stock. Maybe we have, in this case, we have some inflow. Something's coming in. And the amount of the stock affects the openness of this valve, for example. So this is one possibility. Another possibility would be that the stock affects the outflow. I'm going to try writing the word first. So in this case, the level of the stock affects how rapidly the stock decreases or increases. But how, I'm sorry. So let's be clear about this. The stock will increase, as we just learned up above here, right? Stocks will increase based on the difference between the flow in and the flow out, right? Or decrease based on that difference. So what we're saying here, if you think about the difference between these two diagrams, is that something about, this would be like a system, if we use the bathtub example, this would be basically, let's say we considered the physics that the higher the water level, that actually increases the pressure at the bottom of the tub, which causes the water to move out faster. Okay, that would be, that encapsulates this example on the right. Another example would be, let's see, For example, you're running out of money, so you do less shopping. So you notice that your bank account is getting low, and so you decide to do less, to spend less. Versus over here, let's say you notice that your work you're doing is very profitable. You notice you're making a lot of money without doing a lot of work, so you decide to do more, do a little bit more work. So work more. So you're incentivized to try harder. Or another example, maybe the learning you're doing in this class. You're thinking, this is an exciting class. I'm learning a lot. This is going to be useful stuff for my future. So you decide to study even more, which will increase what you know, which will, eventually you could become an expert in systems thinking and get paid to do it. So these are just a couple examples of different way that feedbacks can work. And specifically, and also I'm putting this here so you can think a little bit more about these diagrams, because the diagrams kind of like when you I would encourage you to, as we did in the lab, try drawing these out, because when you see someone draw them out, it can look kind of, you're like, okay, that's obvious. But when you start doing it yourself, like thinking about what is actually the difference between these two things, it makes you think a little bit more. Okay. So there's feedbacks, a little bit more about feedbacks. Feedbacks can cause rapid changes over time, or they can lead to stability of a system, depending on the sort of system or the sort of feedback. So, and there's a thing called a feedback loop. We'll talk about this in a moment more. So a feedback loop is what we call a closed chain of causal connections involving stock. So there's a stock, something which affects something, which comes back and affects the stock. And so there's like basically a loop. So the example of the bathtub wasn't a feedback loop. It was a system where we just have what's coming in is independent of what's coming out, and the level isn't affecting. Most importantly, the level of the bathtub isn't affecting, at least as we described it, the system. So we could think a little bit more deeper about the bathtub, right? Kind of like the beer example in the video, right? At another level, we could include our desire to not overflow the tub, or our desire to take a bath at a certain level, and that would affect our our control of the valves on the input and the output. But the example we gave, it wasn't a feedback loop. So there's two main feedback loops, stabilizing loops, and these go by different names. We saw them in the lab as a negative, which is sort of can be a confusing terminology. So stabilizing loop, also known as negative feedback, balancing feedback. These are just different names for the same thing. Goal-seeking loop or goal-seeking feedback. So these are going to be systems that are kind of drawn to some level, some sort of stable level. So the example that Meadows gives in the book on page 27 is a good example of this. So I'm just going to draw that out. So the example is the energy we have available for doing some work. So that could be maybe we're trying to complete some assignments, or we're working at some job. And so we're gonna consider as the stock, the main stock here, how much energy we have. And we're going to think about the effect that coffee would have on our energy level. So we might, coffee drinkers tend to drink coffee when their energy is low in some cases. So there's some desired energy level. And if the energy level that's desired is different from what's there, these comparing those things, there may be a discrepancy, a difference between the desired level. So, for example, maybe the worker is feeling less energetic than they would like to. So that can lead to coffee intake. And that affects the metabolic mobilization of energy. So coffee itself is not calories, right? It's not energy. It metabolizes energy that the body already has in it. So we have a valve here, and that can cause an inflow of energy into the body, increase the energy that's available. And then that energy can be used this would be energy used. So we use that energy to do something. We're not going to worry about it. And let's not worry for the moment about where the energy is coming from that's in our body. Some food we ate, for example. Okay, so how is this a stabilizing loop? So although we've drawn arrows that sort of indicate a chain, there's these loops can have different qualities, right? I was saying this is a stabilizing loop. So the properties of this here are, so for example, let's if let's say that our energy, we've got a lot of energy, okay? We don't, we're kind of bouncing off the walls. That's higher than our desired energy level, okay? So there's a discrepancy in we'll probably not make the decision to not drink any coffee at this point, okay? So we're not gonna metabolize more energy. Over time, we're going to use this energy, hopefully, to do something productive. And our energy level will come back to some level that we desire. On the other hand, as I described before, let's say that we're pretty tired, then that our energy available is less than we desire it to be. Okay, that causes a discrepancy with the opposite sign, which would cause us in this case to have a coffee perhaps, and get more energy, right? So either way, in one case, the first case I described, if this was our energy, our stock here, this energy available for work, over time, the first case I described, we had too much, kind of comes back to some level that's sort of a desired level. And then the second case I explained, we were low on energy and we used our coffee to increase our energy over time. Okay? So this loop is describing a stabilization phenomena. So something to notice about this. The stocks and flows that are here are level free. For example, discrepancy could be positive or negative. Energy available for work could be, a lot of energy or little energy. So when you draw these diagrams, that's a characteristic of the diagrams. It doesn't say more coffee or less coffee. And this allows the model to reflect, various situations that we might encounter. So we might make this diagram to describe how we want to study more, or how we want to, get some sleep. And it would work for both. So the loop, the stabilizing loop, works to drive the stock, in this case, the energy available for work, in either direction. And we're going to put a B in here to indicate this is a balancing loop. And this was in the video, it was a negative sign. So the B, the negative sign, indicates balancing loop. And balances or balancing loops are sources of stability. They resist change. And again, you could think these could be these qualities of stabilizing loops. You could think of them as kind of helping things in a way that we would like or a way we would not like. So it's just a characteristic of certain types of systems that they can tend to resist change. For as embodied by this diagram we just drew. And that contrasts with the other kind of loop, the reinforcing loop. And these are also known as positive feedback. Or runaway. Many other words for a reinforcing loop. So in reinforcing loops, an example would be the money in a bank account and the interest added. And this was in the Meadows video, so we won't spend a lot of time here. Okay, yeah, so the more money you have, that affects how much interest is added into the account. This is also affected by the interest rate. Depending on the rate, it'll affect how open this valve is. It's money coming from the bank. And so the more money you have, the more interest you make, and so forth, the more money you have in going around. Okay, so this is just one example. So reinforcing loops generate more flow the greater the stock. The more flow, the more stock. They generate less flow, the less stock. And these systems occur when the system question can reproduce itself or grow as a constant fraction of itself. And depending on the situation, a reinforcing loop can cause healthy growth. So, for example, growth of a baby, or person, a young person. The bigger they get, the faster they can grow at least early on. The cells reproduce, or the same behavior can lead to runaway destruction. Let's see. And mathematically, the result of the reinforcing loop is exponential change. So over time, if this is the amount of the stock, it's not just a straight increase over time. It tends to curve up or curve down. Right. So reinforcing loop. Another example would be the capitalist system. Right. The more money, the more power that a company or a person has, the more they can obtain, and the more they obtain, the more influence they have. and so on and so forth. So this is the reinforcing loop is the central engine of how the economies that at least that are dominating the planetary economic system, this is how they are working. More money makes more money. Okay.